Hey folks, Professor Fiore here. We got an interesting one today. We're going to talk about the convergence of LEDs, pulse width modulation, and human visual integration. Now, does that sound spiffy or what? We're going to see something that might surprise you. First, we'll talk a little bit about pulse width modulation. Essentially, it's a way of encoding information, signal levels, things like this, as a series of changing widths in the sequence of digital pulses. So imagine a square wave rectangular pulse train where the width of the pulses changes, gets fatter, gets skinnier in accordance with some other signal. So applications pretty broad. Motors, lights, we can control the speed of motors, the intensity of lights, and we're going to look at the light part of it in this video with an LED. Power supply regulation is another one. Class D audio amplifiers. There's a number of places where we might use pulse width modulation. Typically, you would create PWM as a constant frequency square wave with varying duty cycle. That's typically the way that you would do it. There's another way of doing it, but I'm not going to get into that. This is the most common way. Now, here's where it gets interesting. If the speed of this square wave is high enough, if it's fast enough, and that fast enough is around 30 hertz or faster, what ends up happening if you're controlling an LED is that you won't see individual flashes of the LED. It'll sort of blur together. Your eye will essentially integrate the signal, the amount of light that you're getting over time, and what you perceive is a brightness change. Sounds kind of interesting, okay? So basically, if you haven't seen PWM before, this is what we're looking at. This sort of maroon swoopy curve here, right, would be the information signal or the control signal, however you want to look at that, over time. And then the green pulses, that's the PWM, right? So when the signal is small, we get really skinny pulses. When the signal is large, we get really fat pulses. All right, that's simple. That's really all it is. And what we're going to do is we're going to use this green, right, these pulses to drive an LED or to drive a motor. Right? We'll have a switching transistor, basically. In the case of larger currents, obviously, it'll be a power transistor. But we're going to use this logic signal. I mean, this might be a 5-volt signal. It could be some other level. That's really not too important. Whatever that level is, we drive some kind of device like a power transistor, a power bipolar, power MOS device, whatever the heck it is. And then that current, in other words, the collector current in the case of a bipolar or the drain current in the case of a FET, is what's being drawn through the LED or the motor. So basically, as this gets fatter, we're going to have a brighter LED and a faster motor, right? Faster motor speed. That's the basic idea. So let's go look at the circuit. All right, this is a pretty straightforward circuit you've probably seen before. And if you haven't seen a little LED driver, you need to go back into the playlist here and look at some basic switching applications. Essentially, what's going to happen is we're going to have a logic signal back here. This is going to run between 0 and 5 volts. That's applied to this base resistor. Now, most of that voltage is going to drop across the 2.2K base resistor. So basically, when this is 0 volts, there's no voltage in the loop, so there's no base current, which means there's no collector current. If there's no collector current, that means the LED is off. Big surprise there. Then when the signal goes up to 5 volts, right, we're going to have about 7/10 across the base emitter. That leaves us with about 4.3 dropping across this 2.2K ohm. That'll give us a couple of milliamps. And given the values that we have out here, that'll be enough to throw the transistor into saturation. So the saturation current, IC sat, would be the 5-volt source less the LED drop. And that's going to depend on the kind of LED that you have. So let's say, 2.2 volts, 2.5 volts, somewhere in there. And then, of course, the saturation potential of the transistor, that might be 1/10 or 2 of a volt. So, you're probably looking at low to mid 2 volts taken up, which means probably somewhere in the vicinity of, depending, 2.5 to 3 volts available across R2 over here, right? This is the collector resistor. So we could just use Ohm's law, take that potential, if it was 3 volts divided by 150 ohms, you got 20 milliamps, right? That's the current that we would expect through here. And if this is a standard, red jumbo LED, 20 milliamps is going to make a reasonably bright LED. So when this signal goes to 0, it's off. When the signal goes to 5, the LED is on. And I'm putting in a 5 hertz frequency on this. Now, one of the reasons I'm setting this up like this with these values, and by the way, you can use pretty much any old, LED here, visible, like a red, green, blue, whatever you want, standard LED that's going to have a forward potential of somewhere between, let's say, 2 and 3 volts, somewhere around there. That'll be sufficient. It's simple enough that you could breadboard this. Okay, you can go in a lab. It doesn't need much. You got a very standard transistor, a couple of common resistors. We're going to look at the LED current, but you don't even have to do that if you don't have a meter for that. You can, of course, connect out a little scope. That would be useful to see what's happening with VCE. And then for the generator back here, if you don't have a simple clock type of generator that you can adjust the frequency on, as well as the duty cycle, like here in Tina, I'm sort of creating this. I'm picking a square wave. And what I'm doing is I'm simply setting the amplitude of this to 2.5 volts. That's the peak, right? So it's 5 volts peak to peak. And then I'm adding right here a 2.5 volt DC offset. So if it's 2.5 volts peak, writing on 2.5 volts, that means the negative part is going to be 0 and the positive part is going to be 5, right? So that's how I'm getting a 0 to 5 volt pulse train into here. Okay? Beautiful. All right. So let's just run this up and see what we get, right? Like I said, you would expect when this goes high, LED is going to turn on, we're going to see appropriate current, and when it goes low, we're going to see LED being off, okay? So we'll do a little transient analysis here. I'm going to run this from 0 to 1 second because this is 5 hertz. I want to see 5 cycles, basically. Okay, there you go. I'll put the legend over here. So you can see, okay, right here, that's the VCE, and we're expecting the VCE to go from just about the full power supply, because there will be some potential sitting across the LED. And then pretty much 0, but there will be a saturation voltage, so it won't be right at 0. Like I said, it might be a tenth or two of a volt. Now you could come in here and measure that. So we're getting like 133 millivolts on that. So that looks pretty good, okay? This nice perfect green, kind of olive green, is the generator signal. Way down here is the current. So let's separate these out so we can see them a little better. All right. Oh, that's much better. So here's our VCE as expected, right? Going up to just shy of 5 volts and then down to, nearly 0. And then we have, our generator, 5 to 0, 5 to 0. Burp, 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 burp. LED current, this is coming up to, let's see, that's 15, so that's around 20 mils like we expected. So it's flipping back and forth just as expected, right? The generator goes high, current turns, transistor turns on, we get current flow, transistor's in saturation, it's nearly 0. Generator turns off, so there's no base current, there's no collector current, right? LED current goes to 0. All the voltage, virtually all the voltage is dropped across transistor. And it just continues like this. Right? This should not be surprising at all. So if you build this up, you're going to see this LED blinking 5 times a second, right? Da 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 da. You're going to see this thing blink, 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 blink. There's no way in Tina, unfortunately, that I can get this thing to actually blink. Okay, so that's why I'm saying this is a nice one because it's very few components. This is a nice one to set up for yourself. Okay, now, given that, I'm going to come in here and change the input. I'm going to change this from 5 hertz to 50 hertz. Okay? And we're going to redo the transient analysis. instead of 1 second, we only need like 0.1 second now because it's 10 times faster. And here we go. This should look pretty, similar. I'll separate them out. Yeah, look, it is basically the same thing. I mean, there's some minor changes, but it's basically the same thing. Okay, I can put the legend over here. Okay, there's ILED and VCE and VGen, 5 to 0. Everything's, I'm getting the same current. The voltages, they look pretty much the same, right? You go back and forth. I mean, the display here might be changing some things a little tiny bit, but, the wave shapes are as expected. The amplitudes are as expected. No big surprise, all right? Now, this is kind of important because it is the case that the LED current really is pulsing at 50 hertz. You're getting a pulse, sort of a rest, it's off, another pulse, and it keeps on going like this, okay? But if you actually build this and crank this frequency up to 50 hertz, this is not what you're going to see. You're not going to see this thing flashing really fast because the human eye, the eye-brain combo basically, integrates this over time. So what you're going to see is a constant brightness LED. It's really cool if you have, a generator with you have a frequency knob on it that you can, sort of move in real time. You just start at 5 hertz and just start increasing the frequency, and you'll see that thing flash faster, 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 faster. So it's kind of like going dunk, 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 and then when it gets fast enough, it just sort of, you don't see any more flashes. It's just constant. It's a constant brightness. It's really kind of cool. Okay. After you get to a certain point, right, after you get, past 30 hertz, it doesn't really matter anymore how fast it goes. And like I said, you could stick a scope probe across VCE and you would still see these kinds of pulses, right? You still see this VCE. It really is flashing. It's not like somehow there's some capacitance in here that's sort of averaging things out. The LED really is flashing that fast. Or, it's capable of flashing way, way faster than that. But it's the human eye here that's doing it. This is the same thing that happens when you watch a video. This very video is being recorded at 30 frames per second. So it's really 30 individual snapshots every second. You put them together like that, and it's fast enough, your eye integrates it, and it looks like entirely smooth motion. Yay. Okay. Now, how do you sort of compare this sort of brightness level? Well, obviously on your function generator, if you have a nice square wave out here, hopefully there's a DC, not a DC, a duty cycle control on it so that you can move this back and forth between 100 and 0%. So you'd start at 50 like I have here, and as you crank it up, you bring it up to 70, 80, 90, 100, 100%. These pulses get fatter and fatter and fatter. In other words, the currents get fatter and fatter and fatter, right? These right here. So meaning the LED is going to look brighter and brighter and brighter. And as you go the other way, it's going to get dimmer and dimmer and dimmer and dimmer. Now, if you don't have an adjustable duty cycle, you can kind of do some individual things. Like you could switch back and forth between this and just a fixed 5-volt supply, because a fixed 5-volt supply just cranks the LED on to maximum, right? In other words, there's always base current. The transistor's always in saturation. There's always maximal current. In this case, you're always getting 20 mils. So you're going to have the brightest LED. And then when you hook up a perfect square wave at 50%, right, it's only getting half as much current on average. So you're going to see a decrease in the brightness. It's just a lot more fun if you have a little knob on your generator there and you can control the pulse width or the duty cycle, because then you can just kind of play with that and the thing gets brighter and dimmer and brighter and dimmer and brighter and dimmer. And you might say, well, what's so great about that? Why don't I just turn R2 over here, the collector resistor, why don't I just turn that into a potentiometer? Couldn't I do the same thing? Yeah, that would have the same effect. However, because it's the driving signal, the control signal that does this, this can now be done programmatically. In other words, you can have some kind of controlling circuit back here, like a microcontroller, and you can program what this thing actually does in response to something else. Right? So you have a sensor out there, a sound sensor, a light sensor, whatever, a temperature sensor, whatever it is. And you can use that with the microcontroller to control what the duty cycle is. And now the brightness corresponds to this other variable. Okay? That's kind of interesting. Like I said, this is just, sort of a simplified thing here that you can just very quickly hook up on a proto board. Now, when it comes to a motor, if you had a little DC motor, so you can whip out this and put in, like one of those little 9-volt hobby motors that are about the size of your thumb. If you do that, what will end up happening is the speed of the motor will change. So when you got a big percentage duty cycle here, you're going to have fast rotation. And when you drop it down, as you go 50, 40, 30, 20%, it's going to start slowing up. In that case, the motor is receiving pulses like this, but the motor isn't like slightly turning, stopping, slightly turning, stopping. There's physical inertia associated with this thing, and the thing is just spinning. So it's responding to these sort of nudges. Imagine you had like a wheel, like your bicycle, for example, sitting on a repair stand. So the wheels are free to rotate. It's kind of like you grabbing the wheel, as it's spinning and just giving it a little bit of a nudge. If you give it a big nudge, your hand is on it for a while, you're going to get that thing to go pretty fast. If you're just giving it a little tap every now and then, that's like a small duty cycle. It's not going to revolve quite as fast. All right. So that's essentially what's happening there. There's inertia involved, and it really is sort of smoothing this thing out. Okay. It's just that with the LED, it's kind of fun to do this and watch it go from flashing to just solid, at least what appears to be solid. In my classes, I always would throw in this little idea, which is this is really keyed on the human visual system. We're sort of exploiting something about the way humans see things. What we don't know is if some point in the future we come across some other species, interstellar species, okay, there's nothing that says their evolutionary path would be the same as humans. There's nothing that says that their visual system would be identical to humans. So their integration speed might be a lot faster or a lot slower than ours. In other words, this original 5 hertz, that might look solid to them. We don't know. We have no way of knowing. On the other hand, when I speed it up to 50 hertz, they might actually be able to see that as 50 hertz flashing. So the things that we use, things we take for granted, for example, like a video like this, when they see this, this may just turn into a huge blur for them. It may just be this constant flashing of still images that would drive them crazy. In other words, like you watching an old style video that was done at 5 frames per second. You can kind of see what the motion is, but it's very sort of sticky and stop action. It just doesn't flow. Okay? We don't know. It's kind of fun to think about those things. And this is, like I said, this LED is keyed to the human visual system. The motor, on the other hand, is actually speeding up and slowing down due to inertia. Right? It's not pulsing like this, but the LED is really pulsing. Okay? Anyway, it's a fun thing to do, easy to check. And if you are dealing with the microcontroller, okay, in the playlist, the microcontrollers using C and Arduino, there is a lab number 12, that actually has you do this with a small motor. You can use, like I said, a little hobby motor, or the lab actually has you use a little like boxer fan. So it's a little easier to tell because those little motors, unless you stick a little piece of tape or something on the shaft, you can't really tell how fast it's going. But a little boxer fan, that's pretty easy, right? So you can do that. In that case, I think if I remember correctly, the current demand was a little higher and we had a small power FET in here to do that. But it still would work the same way, all right? But you can always start off with an LED. It's kind of a fun little thing, all right? Okay, try it, play around with it, have some fun. Any questions? You know what to do. So until next time, this is Professor Fiore saying, take care.